So hello all, welcome to session 5 of the Intro to AI-Driven Science on Supercomputers. Today, we're going to learn a little bit more about tokenization and embeddings from Archit Vasan, who is a postdoctoral research fellow here at Argonne National Lab. Additionally, I think we have sort of a cool thing for the science talk today. Instead of being a talk, it's going to be a tour. So we're going to have a tour of the ALCF machine room and supercomputers that Chris Knight, who works at the Leadership Computing Facility and leads the Catalyst team, is going to give us. So that will be a cool opportunity for everyone to ask questions about the machines, specifically Polaris that you've been running on, and any other questions that you have about the facility. Chris is an expert in all things ALCF. So we have to wait, unfortunately, for that. And I'll hand things over to Archit now to sort of get us started on the material today. Archit?
Hey, how's it going, everybody? So today I'm going to talk about, as Paige said, so actually there's a bit of a change. So I think I'm actually going to talk a little bit more about some more aspects of these large language model architectures today, instead of focusing on the tokenization and embedding. But without further ado, let me share my screen and I can walk you through this this discussion that we're going to have. So
before
today,
you get going, will you zoom in a little bit so the text is a little bit different?
Sure thing. Yeah, is that better?
A little bit more?
Sure. Is that better?
Oh yeah, there we go. I think that should be good.
Okay, cool. Okay, so so we're going to be referring to this notebook. So I'll show you, point you to this notebook right here, LLM part 2.ipynb. And so I'm going to be continuing the discussion given by Carlo last week on the large language models. And so we're going to talk a little bit more about positional encoding. So it's going to be talking about not only how are the tokens embedded, but also how do you consider like spatial information about these tokens, attention mechanisms, output layers, and then finally training loops. And so hopefully we'll have provided you enough necessary background for the next week's discussion on distributed training of LLMs. So if you're, so there's just a few things we should go through. If you're using ALCF for the first time, first log in, and you've seen these in the previous sessions. So if you need a refresher, please go over these instructions. And I'll show you an exciting example here first. So this is something that Urban has already given you, or Urban Ramanathan has already given you this discussion of GenSlim, which is a language model that's able to predict genomic information very, very nicely. And it was shown that it was able to learn using a language model how to like identify the evolution of SARS-CoV-2, so to identify different variants of SARS-CoV-2 using genomic sequential data. So now let's get started with the talk of these large language models. So before I begin, is everybody's able to hear me, and they're able if anybody's not able to see this properly or has like a hard time hearing me, please let me know. But if not, then I'll get started with the discussion. So before we begin, just a repeat of previous lectures. Please set up your HTTP proxy on the system, because Polaris you need to set that in order to access like, the internet. And yeah, so please set this before you begin. And so yeah, so now I'm going to give you a little bit of recap from last time, where Carlo talked a little bit about using HuggingFace as a way to use these large language models in practice. And so it's a platform that has a lot of different open source library tools and resources like pre-trained models and data sets So if you want more information about this, you can refer to these two links. But I'll show you two main things that you can do with these HuggingFace models. So one of them is inference, and the other one is training. But before we begin, I'd actually like to issue a warning about these, about especially these HuggingFace models. So these LLMs are really only as good as the training data used to train them, and so they usually scrape through the web to identify, to create this training data. And because this is text data, they don't really have any ethics or judgment or really editing ability within the model itself. And so there's work that's been done to add these into these models, but uh, um, they haven't. I mean, there's always the chance that you might have some generated text that might be surprisingly dark or questionable. And so please run this next cell block at your own discretion. And so I try to keep the input text as friendly as possible, but please, yeah, please run this. And if anybody has any trouble with any of these, with loading any of these modules or running any of these blocks, please let me know in the chat. So you'll see that that it'll generate multiple responses here, and here I can run this for you. It'll generate multiple responses. So I'll just keep talking about this in a little bit more. So yeah, you can see like it'll generate some text that continues the sentence of "my dog really wanted to." And so related to what I was saying last time, or what I was saying is that we'll actually kind of cover these evaluation metrics as well as the safe and responsible uses of LLMs in session 8. And so that's going to cover what I discussed about these LLMs being trained on web data. And so there's some practices that people have been taking in order to make these LLMs as responsible and as safe as they can. Then to shift gears a little bit, the next thing I want to show you is training of these models. And so this is another aspect where you can load in your own data set and train a model with that data. And so here I'm just going to show you the boilerplate code for how do you train these models using HuggingFace. And so what you would do is you would load a data set, create a data correlator for these language models, load in your tokenizer, your model. So this is all stuff that is kind of a repeat from the last lecture. You'll load in the data set, and then you can specify some training arguments here. So I'm just going to go through these very quickly so we can get to the next part of this discussion. You can load in these training arguments and then set up a trainer. And then there's another step where you can actually train a model using HuggingFace. So this is all how these model architectures are actually used in practice. But we want to see what's actually going on below the hood. So really what I showed you here is it's like an extremely useful way of using these models, but it is very black boxy. So it is kind of using this idea of that these models are just things you plug in and you can generate text using them. But we really want to go and dive down and see, and you've also noticed that these models, the text they generate can be a little bit random. And so there's always like, it's really good to understand what is going on in these models so you can understand how to modify these model architectures in the best way possible. So let's look a little bit deeper in the model architecture itself. And so Carlo already talked a lot about tokenization last week. So if you want a refresher on that, like please go back to that lecture because it was yeah, he did a really good job with explaining tokenization at that time. So let's look at how these models actually deal with language. And in order to do this, we were using GPT-2, which is one of the there's like GPT-3, GPT 4.4 available now, but that was that's still a very popular language model. So in order to do this, we can load in transformers, import GPT-2 tokenizer, and GPT-2 LLM head model. And once again, please post in the Slack or post in the chat if you're having any trouble with loading these. Yes, and as was posted in the Slack, please make sure to also use the Conda module, Data Science Conda 2023-0-10, in order to do all of these things. Yeah, please let me know if there's any issues with any of this loading. But I'll keep going with the discussion. So this model actually uses something known as the GPT-2 LM head model. This is the main architecture it actually uses. And so when you print the model, you'll see that there's a series of things that many of them you've heard before. So you've heard what dropouts are, you've heard what convolutions are, and Galoo here is just an activation function. But there are a few things here that you haven't heard about. And so let's look at GPT-2 in a more simple schematic form now. So we can see in the schematic form that GPT-2 is an example of the transformer architecture, and more specifically, it's the transformer decoder architecture. And so what's happening here is that an input token, so the sentence that you want to actually load into the model, it'll be sent into this embedding space. There's going to be some positional encoding happening, and then it goes into this gray block here. And then after passing through this gray region right here, it'll pass into a linear layer, and then it'll lead into an output probability. And so from this output probability, you can generate some kind of word. And you've heard some about this output embedding. So that's what Carlo talked about with token embedding practices. But this part is also very interesting, is understanding what's going on in this, excuse me, in this gray region of this transformer. And what this gray region is this is what's known as the transformer decoder region. And there's also a transformer encoder region, which is slightly different. There's also the transformer encoder region, which is slightly different. But let's talk about this because the transformer decoder is actually, I'd say, more commonly used nowadays. And so what this is it's actually consisting of what's known as these decoder blocks. And each decoder block is taking in a word. It's learning something about that word or that token, and then it's spitting out some kind of additional word. And so in this example, you have this sentence, a robot must obey orders. And from this transformer decoder, it's able to identify the next word as orders. And so to dive even deeper into these decoder blocks, you see that the main two layers that they're made up with are the masked self-attention, as well as the feed-forward neural network. And so you've heard quite a bit about feed-forward neural networks in the previous discussions that you've had in the previous lectures. And so to review them, you can look at this previous lecture series by Bethany. But here, what we really want to do is we want to discuss these self-attention layers. And arguably, this is really what sets these transformers apart from these different architectures, is how the self-attention is actually like what it's actually doing to these sentences and how it's actually reading these sentences into the architecture. And so before we begin, let's set up some imports that we'll need. So these are just a few. So you just want torch and you want torch neural network here. You also want to import this functional as SF. And I'm just setting a few hyperparameters that we might need for the rest of the talk. So now let's talk about these attention mechanisms. So you've learned about embeddings of words. So you've learned about how are words actually Like, how do you get the meaning for individual words? So how is it that you can take a word and you can understand the meaning behind it? So these are these embedding layers that Carlo talked about. And so if the model did a good job in the token embedding, it should know like what are all the words in a sentence. But let's then say that let's say like I were to ask one of you, the animal didn't cross the street because it was too tired. Something else that a human will understand about this sentence is not only what are all the words meaning by themselves, but also what do the words mean in the context of other words. And so you can take words like it, for example, for example, and I can ask you the question, what is it referring to? So what does it mean? And the answer then would be, it means the animal. And you can also ask a human, what is the state of it? So what kind of state is it in? And you can see that because you have this human intuition, you can say it clearly means tired here. And you're not just getting this from the meanings, you're getting this from the context of that sentence. And finally, you can also ask the question, what is the action for it? And so its action is didn't cross. So we're able to do this just intuitively, but we want to know, how is the model actually able to do this? And so in order for the model to actually learn this, it needs a simple yet generalizable algorithm. And I'm going to reiterate, what really makes these transformers really powerful compared to the earlier sequential architectures is how it encodes this context with the self-attention mechanism. And so there's other types of attention mechanisms, but I'm going to focus on this one because it's the kind of the most standard most standard type of mechanism. So what self-attention is doing is it's taking this sentence, something like this, and it's looking at the token, it, and then it's establishing some kind of its context with the other tokens within that sentence. And so these lines are the context of these of the words in relation to it. And so you can see that there's a lot of context between it and the animal, or the it and I guess this word didn't also, there'd be some context. And so the way that this works and the way that this is like, it's actually a very elegant way that this is actually calculating this context. So what these self-attention mechanisms are actually doing is they're encoding each of these tokens with three vectors. And so these are just three ways of talking about these three vectors. There's query, which is kind of the word representation that we score these other words based off of. And then each of these words will also have a key, which is going to be the label for that word in the sequence. We can match that label to each of these queries. And finally, the value is going to be the actual word representation. So it's going to be the actual word itself. But let's look at this in a sort of crude analogy given by Jay Halamar's famous notebook. And he likes to think of this as using as like maybe an accountant looking at different files. And so let's say there's an accountant and he wants to look up my file. And so what he would have is he would have a post-it note with the file, a post-it note that says the name Archit. And so then he wants to take this name Archit and he wants to match it to a file that has maybe my last name, Vasan. And so the Vasan would be a key that he'd be looking for here. And so then he'd go to his file cabinet and he'd see that, okay, these are the tags on these files. So let's take this query, Archit, and let's look at the keys and see which one matches to Archit the best. And he'll see that, oh, hey, key 2 matches Archit. And so now let's open up that file and let's see that what's the value. So what are, like, let's say I'm doing my taxes. What are my documents that I need for my taxes? So this is in a way how these attention mechanisms are actually working, is that taking they're taking these queries and then they're looking at the relation between the query and the different keys. So the query and all of the keys, it'll calculate a score between these. And then using that score, it can then weight the values, and then it can send those values deeper down into the architecture. So let's talk a little bit. So in order to encode these into the model, you can use these keys, these queries, and these values as, so we're just using here as linear layers. And so essentially it's just a way to have something that has like a series of weights that are tunable within the model, because the model will actually be learning the best way to encode these different vectors. So now let's dive a little bit deeper into the actual algorithm, and if there's any questions that you have, please also let me know as we go. So let's look a little bit deeper into the algorithm. So I showed you in a nutshell, I mean, I showed you kind of an overview of how this is working, but we can see that the math actually matches this analogy pretty well. So really mathematically, what's happening is you can take a sentence, let's say you have a sentence of 2 words, thinking and machines, and you can, so there's this idea of embedding these different words. So you can embed the word thinking, and you can embed the word machines, and then you can calculate these queries. So these queries are, once again, if you look right here, the queries are the word representation that we're using to match to other words. So that's going to be the query right there. And the key is what you're using to match with so the key is what you're using to match with that query. So that's going to be a K1 and K2. And so since we only have 2 words here, this is going to be the keys that we're matching our queries to. So then we can also establish values. So the value is just going to be the representation for those 2 words. We can then multiply the query by the key. So do a matrix multiplication here, or sorry, a vector multiplication here, and then you can multiply this same query by the other key and get another score. So now you have 2 scores. You can divide by, so you just divide by the square root of the dimension of these vectors. So this is just, it's been shown that this helps experimentally to improve the gradients when you're actually doing training here. And then you can then calculate the softmax. So the softmax, I think you've heard about this in the previous lectures, but this is, if anybody of you is in like physics or biology or chemistry, any of those kind of fields, you'll know that softmax is essentially just, it's similar to like a Boltzmann weighting. So you take this thing as an energy, you Boltzmann weight it, and then you multiply by all of the values. So you have softmax times value 1 and softmax times value 2. And then you can sum these things together and you can get, I like to think of this as a partition function, if you're familiar with like uh, statistics. And so this is kind of a partition function which takes into account both the value of each of these words as well as uh, the relation between the query and the keys. And so now you're going to have your partition function for or your z-score for each of the words. And we can look at this in the code, and it's performed in a, I mean, it's performed according in the same way as it's shown here. So we can see that you can define your test vector. So let's say our text vector is x, and we can also define the head size. So the head size is going to be the size of the vector that we want to return. We can define the key, which is going to be the key layer that we're using to actually create the key for all the words. We can create the queries and the values. You can see here. And then we can then apply these different layers onto the test vector that we have here. So we then apply this and we get the key vector for that particular word, the query and the value vector. And then we can then plug this in and calculate the score. So the score is, if you remember right here, the score is going to be this guy right there. So we're going to be calculating that for this combination of two things right there. And so this @ symbol is able to do so it's doing some kind of vector calculation so that we don't have to actually write out all of the calculations here, but this then will create a matrix that has all of the scores for all of the query key combinations. We can then take the softmax of this and then multiply the softmax. So this is the Boltzmann like softmax calculation, and multiply this by all of those values. And this will give you the output. This is the output that's going to be the output for this whole sentence that you're inputting in. And so we can print out this sentence, and we can see it gives you a vector. And so this isn't really meaningful as of now, but I'll show you something that's pretty cool that will allow you to actually to visualize these attentions. So this is, I just showed you self-attention. So this is how these models are actually able to get the context between the different words in a sentence. But this is a relatively kind of I'm not going to say simple, but it's a relatively like kind of simplified way that this is done. And typically in practice, these models will actually not just use one self-attention mechanism, but they'll actually use multiple self-attention mechanisms in parallel. And this is called multi-head attention. And so this is done because you don't want, let's say you have a word like, let's go back to this example. Let's say you want to go back to this example of this word, the animal didn't cross the street because it was too tired. And so if you just use self-attention with one head, what you might end up seeing is you might end up seeing that the word it would have most of the attention with itself. Because that's kind of the simplest thing for the model to learn is just, okay, this word is like has context with itself. But actually, what you really want is you want the word it to have context with the other parts of that sentence. So in order to do that and to maximize the probability that you're actually going to get that, you're actually going to see those attention mechanisms actually make sense. I mean, like that attention mechanism actually encode for the context. We want to just do this a bunch of times, just do the attention a bunch of times, and then like add them all together in a certain way. So this is why we use these multi-head attention mechanisms. So just to quickly go over how these things are actually working, let's say you have an input sentence, thinking in machines. We could embed, okay, we do the embedding as you know, and then we can then split this into multiple heads. So we can split this into these 8 heads. And we can we have these the weight matrices for the query, the key, and the value, and we can multiply the x by each of these weight matrices, and we can get the attention using the resulting q, k, and v matrix for all of the different heads. So this is basically just the same word, same sentence, but we're doing this a bunch of times. Then we can calculate this z-score for each of these heads, and then multiply this by a weight matrix. And then we can get a final z-score for this sentence. And so this is basically it's giving us the same output as the self-attention mechanism, but it's just adding in the stochasticity into this example. And so now that I've shown you this, this part is, I think, is really cool. We're going to actually look at these attention mechanisms, and we're going to see how this actually works. And so what we're going to be using is we're going to be using something called BERTviz. So this is a very powerful visualization tool. And this will show you how exactly these models are actually are actually using these heads, and like what the attention mechanism is within each of these heads. So let me know if any of you are not able to load in this tool, BirdFizz. I included so I have a little bit of code on how to install it here, but I also included the source code. And so um, try using it with the source code to see if that works for you. And if it doesn't, then please install it yourself. But I'll walk you through this, and you'll have some time. You'll have some time to play around with this later. So what you do is you load in the model name. So you can load in GPT-2. And here I'm going to be using an input text. So I'm going to use "No, I'm your father" from Star Wars. I mean, I'm sure, hopefully that's not a spoiler for anybody here. And you can then load in the model. So just the auto model for causal LLM from pre-trained to the pre-trained model, the tokenizer, and you can encode your inputs with the tokens. And what's important here is that the model will have the output attentions equals true right there. And you can get your outputs from this model. And you can access the attentions using this key right there. And then there's a couple more steps here, and you can load in this thing model view, and it'll let you see now the attention as well as the tokens. And so now you can look at these different heads. So once this is loaded for you, you'll see that it'll create this really cool looking table with a bunch of heads as well as a bunch of layers. So these layers are going to be the different decoding blocks. So I talked about how you have different decoding blocks in this transformer decoder region, and you also have these different heads. And so what you can do here is you can actually click on these different heads, and you can directly visualize the attentions that you're seeing here. And so this is really useful because I mean it's really useful to see what is the model actually doing here, because it's very easy for you to just think of like some of this detail, but it is very much of a black box because the model is just being trained, and then you just kind of look at these scores about how it's actually dealing with the data. But by actually looking at the attentions, you can actually see what is the model actually, what is it actually learning within these sentences. And you can also see here, it really illustrates why it's important to have multiple heads. Like, let's say we go to this example, you can see that if you look at these attentions here, so you can see no has most of the attention within this head just to the word no. This has most of attention here, this has most of the attention here, and so on. So that's why it's really important to have these multiple heads you can see here, because yeah, that's why it's really important to have these different words here, because you can yeah, to have all these different heads, because you're increasing that stochasticity of these attentions. So for example, here you can have maybe something where no has a lot of attention with different parts of that sentence. Here, it's learned something where there's basically no attention for any of these other guys. Here, it's also no attention for any of the other guys. And so you can see that it's actually kind of funny. I don't know why this is happening, why the word no actually has a lot more attention with everybody except for besides these guys. And so this can also illustrate maybe some kind of limitations with that model, where you can see that, oh, hey, for these kind of tokens, it's really being dominated by these, like that's really dominating the attention as opposed to the other guys. But you still have examples where you do have attention to other places. And so at least you have that stochasticity, and you have that ability for the model to actually do the learning. So this is a really, I mean, I'm going to give you some more time to play around with this. I think we have a break at some point, but I think this is really cool, and it's actually this kind of mechanism is very applicable in a lot of different like science applications. Like you can take, let's say you're trying to study protein-protein binding, and you have a model that can just predict that, hey, these two proteins just bind. You can maybe use these attention mechanisms to actually look at and to see what are the residues of those two proteins that actually bind to each other. And so this is a really cool uh, analysis tool. I think actually I'm looking at the chat right now, and I see Nicholas has a very interesting question. So he's asking if there are any mappings in here to any parts of the speech, such as the assertiveness of a proposition of no in the statement. So that's actually interesting idea. I don't think that the attention is doing that, because the attention is just going to be getting the context between that and other like words within that sentence. There might be ways of analyzing that using maybe different prompts that you feed in, but I honestly don't know in this context. Okay, but yeah, I think I'm gonna move on with talking about these attention mechanisms and go on to positional encoding, which is it's different from attention because arguably it's you could say it's kind of a simpler kind of thing that these models need, but positional encoding is so yeah. Let me back up a little bit. So we've already discussed token embeddings. So Carlo discussed that last week. And we just discussed attention mechanisms. And so this is going to allow for the context between your different words. But another question we should probably ask is not only how do we account for the context between these words, but also the order of the words in some kind of input sentence. And so let's say we take these two sentences, the man ate the sandwich or the sandwich ate the man. So they're clearly different. And so the model is, so it's learning the words, and then it's also learning the context. But really the context is just saying, what is this word related to this other word? So what is man related to sandwich? Or what is sandwich related to man? As you can see that these words are definitely related to each other in an attention mechanism, but probably these words, and I'll actually ask you to do this. This might be kind of an interesting experiment to see if the attention mechanisms for these two sentences are the same in this thing. Because I feel like they probably will be. But that's why you also have to add in something known as a positional encoder here. And so this positional encoder, and I'm going to kind of go through this a little bit quickly. The positional encoder is basically a way, so it's basically just a vector that you add to the input embedding. And so you can take a sentence like the quick brown fox, add it into this embedding model, and you can then take the order of this sequence and add it into the positional encoding model. And if you add these two vectors up, then this will allow you to encode both the embeddings as well as the positional encodings into that model. And then you can then feed that into the rest of the transformers. So in this example, we're setting up these positional encodings similarly as the token embeddings. So we're just going to be using the nn.embedding tool, which is essentially just a lookup table that Torch is using in order to create these embeddings. But in practice, they're actually much more complicated. I wouldn't say much more, but they're more complicated. So in practice, these positional encodings will use things like sinusoidal functions in order to map on the value into a certain place. And if you want to read a little bit more about that, then please refer to this this blog. There's a lot of blogs about this, but I found this was one of the nice blogs to refer to. So, and this is how we're going to be doing it. So we'll be just taking a vocab size of 65, so just a random size that I made up, and then embedding a layer of 64. Once again, just something I made up, and then set this this token embedding table the block size is going to be the maximum context length, so like the sequence length, and then the position embedding table, which is this embedding table. And so you'll see that there's two values here. There's the n embed, which is going to be the actual embedding layer dimension, and there's also the vocab size, which is going to be the size of the vocabulary that we're using to get these token embeddings. And we use something very similar for the position embedding table, where we can just use the block size, which is the context length. So it's just going to tell you where is this part of a sentence in the context of those other sentences. Sorry, within that context of that sentence. So yeah, we can look at how these things look. So we can look and we can see that these. So let's just take a random example of a tokenized vector. So this is just tokenized where 1, 3, 15, so on, just map to the index within the vocabulary. We can look at the token embedding table, which is tokenizing these in such a way that words that have similar meaning are close to each other. And we can also look at the token and the positional embeddings. So for the same vector, if we add these things together, we can see that this changes these vectors slightly. And so this is essentially just taking 2 points in this vector space, and right now they might be close to each other if they're, or if maybe let's say further away from each other if they don't, if they have different meanings, but they may be pushing them closer to each other if they're commonly together in a sentence. So like, let's say the dog might be very close to each other in a sentence because they're sequentially next to each other, but they have different meanings. And so this way it's allowing you to actually account for the fact that those words might actually be very close to each other in an actual sentence. And so during a training process, these embeddings can be learned to best encode for the token and positional embeddings of these sequences. And so let me ask Paige, so should we do the tour at the end of my lecture, or is there like, should we do it within, like during a break, or
That's a good question. It'll be at the end. So the tour will
okay.
start at 4:10.
Okay, perfect. Then I'll just keep going then. So now I've talked about, so we can go back to this this architecture, and we can see what have we learned about so far. So far you've learned about how are these words embedded into embedding space, both based on the tokens and based on the positions. Then you also learned about how they're how you do self-attention. And there's one little extra detail that I didn't include in these talks because of time restrictions, but these self-attentions are actually being done in a masked form. So this would be masked because we want to spit out new words, and so all we're doing is we're just not looking at the attention for the entire vector and just the tokens that are coming before a new token. And so there's a lot of like if you read the Illustrator Transformer, the Illustrator GPT-2, they'll talk about this kind of minor difference in a little bit more detail. So we've learned about what self-attention is, and we've learned about, you've also learned in the past about feed-forward neural networks. And so the last thing that we should talk about here is how do we actually output something? So once we go through this feed-forward neural network, we're left with a vector. And so we want to turn this vector into a word. So how do we turn a vector in some weird embedding space into an actual word? So we can use a final linear layer as well as a softmax layer. So what the linear layer can do is it'll project this decoder stack output. So remember, the decoder stack is just that stack of a bunch of decoder blocks. So it'll project that vector into a new linear layer. And this linear layer is going to then output this into something called logits. So logits it's just a fancy word for just saying that you get a score for all of these words based on the vocab size. And so you have like, let's say you have like, I don't know, 20 words in your vocabulary. In practice, you have like probably tens of thousands of words, but let's say you have a certain number of words in your vocabulary size, or in your dictionary, let's say. And actually, really what this is saying is then, where is that, like what is the score for that vector within this logit space? So you can then take these logits, then plug them into softmax. Remember, softmax is just, it's like a function just to give you probabilities as a way to think about it. So you can plug it into this probability function, and then this will then give you the probabilities for all of these guys, for all of the different words within your vocabulary. So you can say like, let's say you have only 5 words here, like your words are the, dog, house, big, and blue, or whatever. And so you can get a probability of like 0.1 for the, 0.2 for dog, and maybe, I don't know, 0.4 for house, and maybe 0 for this, and maybe, I don't know, 0.1 for this. And so then you can just pick the cell that has the highest value, and you can then associate that word, which is going to be, let's say, this word, dog, or am. And so this is the way that these neural networks will take these abstract dimensions, these abstract vectors, and then give you some word that actually makes sense. And so one more question is, so we have these models, and we kind of know like these models kind of look like this. They're pretty powerful because of how these architectures are set up, but still, if you just take a model and you just run it as is, it's not going to be giving you the like the answers you're looking for, just because it doesn't know any information about anything. And so you've probably you've heard a lot about training these models, and so you have to do a similar thing here in order to actually train these models and improve the model itself so that it can best encode the context as well as the meaning and the positions of these words. And so a very like kind of intuitive way of thinking about this is what the model is doing is it's outputting these probabilities. So you have these kind of these probabilities right here. And you actually have a ground truth probability as well. So you have the ground truth probability you know for these sentences. So those are going to be the actual logits, the actual probabilities. And so what what you want to do is you want to take, so let's use this as an example. You want to take a phrase like je suis étudiant, and let's say you're training some kind of translation problem, and you want to translate that into I am a student. You can take this phrase, go through the model, and output I am a student, and then you can look to see what is the probability for the outputted vector at position 1. And so in the ground truth, you want that vector to have that thing to have a probability at this uh, kind of value. So you want there to be a 1 at I. You want there to be another 1 at am, another 1 at a. So you're creating the sentence I am a student at the position 4. Position 5 would be end of sentence. But in practice, what you're actually going to be getting is you're going to be getting a series of random probabilities, and you're just kind of tuning the model so that you get the probabilities you want using this kind of idea of backpropagation that you've learned a lot about throughout this series. Specifically, the loss that you'll be using to actually do this is cross entropy. So basically, this is just taking the two distributions, and it's just calculating the difference between the distributions in a very kind of not like a very elegant but sophisticated way. And in practice, what you're going to be doing is you take the logits that you're predicting from your model, so like these guys, the targets, which is the actual values, and then you can just calculate the cross entropy between them, and that'll give you the loss. And another metric that's commonly used in LLMs is perplexity. And so this is actually used, so this is used very commonly to train these models, but this is used very commonly to describe how good a model is or bad a model is. So intuitively, you can think of perplexity as meaning surprised. So how surprised is that model by seeing some new data, for example? And so the lower that perplexity is, the better the training is. So it's very similar to the loss, that if you have a high perplexity, that means that the model will, it's not very well trained, and so it'll be very surprising new data. And mathematically, it's just going to be the exponential of the cross entropy. And so you can take, I mean, you can just take torch that exp, and you can get that, multiply that to the loss and get the perplexity here. Okay, so the final, I think I'm running a little low on time. So the final thing I'll show you is putting everything together and training a mini LLM from scratch. So we can then reset our hyperparameters, which are batch size or block size, and some iterations, learning rate, embedding layer, the number of heads you're using, the number of layers, as well as the dropouts. So the dropout rate, we're just going to use 0 here, so no dropouts. And we're going to be loading in a data and creating some training and test data sets. And so I have in here this dataset/input.txt here for you guys to play around with. This is just a tiny Shakespeare dataset that I downloaded for you. We can just do a simple character-based tokenization and create our training data and our validation data, and then create a data loader here. And then we can set up the components of the decoder block. So these would be the head. So this would be one self-attention mechanism. So you're setting up your key, your query, and your value, which are the different linear layers. And you can also set up your forward for this, which is just going to be multiplying these keys together. And this is the part that I was telling you about earlier that I didn't really talk about in too much detail. And this is called the masking. So this is basically just masking it so that you're only looking at keys that come before a particular query. So yeah, just read a little bit about this if you want some more details about masking. Then we take these weights, and then we can then plug them into the softmax, and we can then multiply this softmax by the output, and then we have the output for that attention mechanism. And then we can then go into the multi-head attention, and really all it's doing is it's taking a bunch of heads. So you have however many heads you're training. So let's say 4 in this example. You have your projection there, which is just combining those heads together. And you have the dropout, which in this case is just 0. And then you can concatenate them all together and then just project them with that linear layer in order to create the multi-head attention layer. Then you can then we're also going to create a feed-forward network, which you've you've heard a lot about these feed-forward networks. They have like linear layers, activations, and then like dropouts and things like that. And so finally, we can then combine all these components into the decoder block, where we can, it's basically just, we start out with a multi-head attention, we then feed this into the feed-forward layer, and there's a couple other things called layer normalizations. So I'm not going to cover that in detail here, but please refer to the Illustrated Transformer, which has a lot of details about that. And then you then can feed this forward, and you can create this decoder block. Oof. And finally, we have all of these pieces. We have the attentions, we have the feed forwards, and now we can then just take these decoder blocks and then just plug them in with the token and the position embeddings. So we can take this token embedding table, this position embedding table, and then plug these in together and create our blocks. And then we're just going to be calculating the token embedding plus the positional embedding. And then after then going to the decoder blocks, we can then get our logits, where our logits are basically just those like kind of vectors that we're going to be turning to probabilities. And we then can just train this using cross entropy between the logits and some targets that you're giving it. And that's kind of the way this is working. And in order to generate some new text that we want to actually generate, we can plug this in, and we can let's go down here. We can get probabilities, let's say, for some kind of text that we're loading in, and we can sample from the distribution some new samples. And so we can then append those samples to a running sequence. So it's a different way to do some generation. So at this time, it might be, I don't know if they need to go with you, or if you're going to start your tour page, or if they have some more time.
So we'll have another 15 minutes before the tour now.
Oh, perfect. So then, perfect. So then, so yeah, I'll just, let's say, let me talk to you a little bit about your homework, and then it'd be really cool if you go back and you start working on this, maybe you start playing around with this attention mechanism. So yeah, let me talk to you a little about your homework, and then you can go back to playing around with that cool tool. So what I want you to do is, I kind of talked to you about how all these pieces fit together, but I really want you to, in your homework, to actually go in and create your own training loop. So actually train these things with a certain number of evaluations, or a certain number of epochs, and to actually get a model that's actually kind of functional, and show how the training and the validation perplexity is changing over your different steps. And so this function is probably going to be very useful, because it's going to help you calculate the losses as well as the logits that you get from this model. And I also want you to play around with this this training loop, but modify one of the hyperparameters from this list. So you can modify like the number of heads that you're using, or you can modify the number of layers that you're training, or even the embedding layers. So just see how changing these different hyperparameters are actually changing these models. So this is a way of kind of, you're really creating your own language model, and you're trying to see like, how do people, when they pre-train their own model, what are they thinking when they do this? So I want you to just run this a few times with some different value, and plot the perplexity over each training step. And as a bonus, if you're interested, you can also output some generated text from each model that you train. And it'd be really cool to see if like there's certain hyperparameters where the output that you're printing out actually makes more sense than others. And another bonus will be to take some other models. So take a more complicated model than GPT-2, such as the recent Llama model, and see how the attention mechanisms might be different there. And so now we still have some time for this session. So I'll ask you guys to go back here to this thing, so this tool, and play around with different prompts. So I think I offered a suggestion. Maybe first you can try playing around with these two sentences. So try playing around with these two sentences first, and then just play around with whatever prompts you want to in this section right here. And you can even play around with different models. If you want to go to HuggingFace and plug in your favorite models, you can yeah, just kind of go crazy with this tool. So I'll give you some time to do that. And also, if you have any questions, please feel free to ask them, and I can take any questions at this time.
Great. We can come back maybe in like 7 minutes, just so there's a chance if there are anybody for any final questions before we transfer over to the tour.
Maybe
Hi,
it was
Chris.
muted. Oh no. Hello, everyone. Should I just start talking, Paige?
Yeah, I think one thing to do is maybe, so I guess one, Archit, you can stop sharing your screen. Perfect. Two, what I'm going to do before we get started is I'm going to spotlight you so you're very big, which I know is your favorite. And then three, I think maybe introduce yourself about sort of like who you are, how you sit in the facility, why you know all of the things that you know. And then we can sort of go from there.
Okay.
For folks, who have questions, feel free to drop them in the Slack chat, and I will sort of act as the voice of questions as they come up.
Okay. Yes. So I guess to start, I mean, hi, everyone. My name is Christopher Knight. I'm a computational scientist. I'm here with the Leadership Computing Facility and also the computational science division we have here at Argonne. I work, I'm one of the team leads for the science team within the ALCF. And so this is a group of computational scientists from across a variety of science domains, chemistry, materials, engineering, physics, that works closely with researchers who are on the system, the resources that we have here at ALCF. And so we work very closely with them, me, but also the data science team, the performance engineering team, really multiple teams within the ALCF. We work very closely with the researchers to help them get onto the system, compiling their codes, running their codes, submitting jobs. Are they getting the correct answer? Are they getting the expected performance? And if not, to help them resolve those issues. And so really a large, as impressive as these machines are that I'll show you, there's an equally impressive human element to this of support that we offer to research teams. And so, to be honest, this is my first virtual tour. And so I went back and forth with a few folks, Paige included, on how to go about this. And so what I have a plan. And what I ask though is, you know, for folks, if they can offer feedback to Paige and company, I would, and so that they can get that feedback back to me and others who are planning these tours, I would really very much appreciate that. And so to kick things off, okay, so, you know, one of the things, you know, so I asked myself the question, you know, if somebody is not actually physically here, what is it that they're going to miss? And so one of the things is missing walking into the data center itself, where it's really loud, because a lot of the production systems we have are air cooled. And so hopefully you see a video that hasn't started yet, but you can see it's big enough. If there's not, Paige, you know, please interrupt and we'll fix it. I do not know if you can see my mouse cursor,
We
but
can.
there's a set of white racks in the immediate front. That's the Theta GPU system. And so this is a set of GPU accelerated nodes, A100s, similar to what I think that you all are working on today, that we acquired as an addition to Theta. And Theta itself is the backside of it are these black racks here. So play the movie. And thank you, the sound is off. So it's really loud in the data center. So I was hoping the sound wouldn't disturb you. But so this Theta is two racks of K&L CPU processors, Knights Landing processors from Intel. It came online around 2016. Unfortunately, we just decommissioned this. And so these machines, they have a lifetime of 6 to 8 years of productivity. And it's not that they are no longer useful for science when we turn these machines off. It's just that there's newer technology that we can make room for. And this, I'll speak to this again when I start talking about Aurora. But Theta itself was at the time a reasonably large machine, some 4,000 CPU nodes with total peak performance that was comparable to an older machine, Mira, that had a much larger footprint. So we effectively took an older machine, Mira, that was some 50,000 nodes and effectively shrunk it down to 4,000 something nodes with a similar level of performance. So that's one of the reasons why we decommission these machines. But Theta, one of the missions for Theta over its lifetime was to help us, the ALCF, prepare for Aurora, and very much in terms of it helping to enable some of the diverse science questions that were being asked on HPC resources at the time. And this is where some of our work as a facility of how to scale AI and machine learning workloads started. And so that's where some of the work, Theta was helped to initiate some of that work at scale for us. And very much a lot of that work continues on today with the AI accelerators and Polaris. So the next movie, no. Okay. And so basically what I did was, you know, from that shot of Theta, I turned a little bit and now we're looking at the backside of Polaris. I always start with the backside of these machines for some reason. And And so Polaris is our current production system. It's an NVIDIA A100 GPU-based system, 560 nodes, each with 4 A100 GPUs, and so in excess of 2,000 GPUs. And so really, this is our main workhorse for teams who are active on at the ALCF through. Sorry. Pause. So this is our main production resource right now, and really this is the main resource for teams who are getting ready for Aurora but who don't yet have access to Aurora. This is the primary vehicle by which we can engage them. This has also been an extremely useful resource in recent years, again with scaling up of AI and machine learning workloads, data intensive workloads, in addition to the more traditional simulation workloads, and really helping to enable researchers that have combinations of those three in their workflows, where they're not just simply running a single code, they have multiple codes of different flavors all running together on the system. And then one thing that I need to do a better job of is that there's a lot of neat science images on the machine, and then we really we create these skins, if you will, around the time when the machine goes into production. And so on Theta, I can say that a lot of the science images there were driven by more traditional simulation codes and workflows. For here with Polaris, I am pretty sure that there are some science images that are now that were driven in part by machine learning. And I think that's going to be very much the trend. When we get the skins shown on Aurora, it will be very diverse in terms of traditional simulation have been enabled by, and also machine learning and data intensive workloads, which I think is a neat thing from a historical perspective. And then from Polaris, I don't know why this starts in black. I'm going to pause this a few times. And so, sorry. Where'd my pause button go? All right. So this is a collection of the AI accelerators. And so that in addition to what I refer to as the production systems, we also have the AI Testbed, which is a collection of different AI accelerators from a handful of vendors that we make available to researchers. Grok, Cerebras is around the corner. And then Samanova and I'm blanking on the last one, GraphCore, I think, yes. And so this is a collection of AI accelerators from the different vendors that researchers can get access to explore the potential benefits of accelerating their AI and machine learning workflows. One activity that's ongoing is also trying to understand how traditional simulation algorithms perform on these accelerators, and the potential benefits of not only accelerating the time to solution, but also improvements in energy efficiency, which is a very hot topic for us nowadays. And so then next is the Aurora system. And so I'm currently in the Aurora reveal space here at the Leadership Computing Facility. And so this is a big open space that is open to the public. And so anybody on site, on campus, if they wanted to, they can come up and walk and take a look at Aurora, which is sitting behind me. So it's not every day that you have a 2 exaflop PEEP system just sitting right behind you. I do have pictures and movies I can show. One of the things that I'm appreciating in this first attempt at the virtual tour is that you really don't appreciate how big this system is. I will hopefully impress upon that in the video. And so at a very high level, and again, if there were questions, please interrupt me, Paige. Aurora is currently the main production, well, not production yet, but it's currently the main system that we're helping to enable researchers to use. It's more than 10,000 nodes of Intel CPUs and Intel GPUs. I didn't want to get too far into the details unless folks asked, but really there's a large number of resources here, and that's really the key takeaway. More than 60,000 high-performance GPUs, more than 20,000 high-performance CPUs, a lot of memory bandwidth, a lot of networking capabilities. And so really there's a lot of performance packed into this machine. And together with the software stack is really helping to enable and will enable, again, more traditional simulation algorithms, but also machine learning and data intensive workflows, and really various combinations of those. And if you were here in the reveal space, we have one of the nodes sitting on a table. I have it next to me, but but you can't really get a good view of it, and so that's why I opted for the image. And so this is on the table that's available, and so people can poke and prod it. It is heavy though; it's around 70 pounds. The red boxes towards the right side outline the 6 GPUs, the 2 CPUs in the middle, surrounded by the DRAM. And then at the end, those big green silicon boards, those are the networking hardware. So that's what's connecting this node to every other node in the system to make it a supercomputer. And then maybe the one detail on this is the cold in and the hot out water supply. So this is a water cooled system, and that's really one of the neat things, I think, which I will show in this video as I switch screens. Bear with me.
So one question, Chris, just for the scale of the node, like, how big approximately is the node compared to like your hand or other previous nodes and systems that we've had before?
Yeah. So bear with me. Hope don't get motion sickness. I mean, that's my hand. Maybe it's the size of one GPU.
Mhm.
6 GPUs on it, the 2 CPUs, the memory, the networking hardware, all these white tubing, that's for the liquid, the water coolant. So there's water flowing through each and every one of these white tubes in the board.
And all told, it's something like 70 pounds, right? And then we
Yes.
multiply that by 10,000 or so, and then we put it in a machine. So the machine itself is also very heavy, along with being very big.
Yeah, so this is a very big machine. It's a very heavy machine. There will be a part in the Aurora video that I'll show. When walking next to these racks, like if we had walked past Theta and Polaris, they're taller than me, and I'm a pretty tall guy at a little over 6 feet. And so, I kind of look up a little bit to see the top of Theta and the top of Polaris. Aurora, I have to look up even more because just even the individual racks themselves are huge. Where did the video go? Okay, so this is a video on YouTube that I'm showing, and so that's maybe as a plug that there's a lot of content we have on the ALCF YouTube channel, if that hasn't been mentioned. And so this is literally the area that's right behind me, just on the other side of the glass. If I play it just for a little bit, one thing that you can kind of notice is that this looks like just a big box. It doesn't look like 8 separate blades. And so this was at a time before we had the compute blades installed in the machine. And so it was only last June of 2023, that we had the last blade installed. And that was the first point in time where we had every part installed in the system at one time, where we could actually try to make it run together as a single unit. And so we are very much in the process of trying to get it ready to behave as a single unit. Which is referred to as the acceptance period. So all of those red and blue tubes are the coolant loops pushing water through all of the compute nodes, and then lots of close-up shots of the networking. I think you probably get claustrophobic if you walk down some of the rows. And then there's one spot where we have somebody standing next to the rack. That's what I'm looking for. I want to make sure I don't miss it. Actually, you can kind of get a sense of the scale here, this person walking through, that there's compute nodes above their head. Yes, and so I'm going to pause it on Beth. And so, she's, I don't know, 5'6" maybe. And so there's a good gap between her and the top of the machine. So these are massive, massive compute, massive resources. And so really, why do we have this massive installation? And so that this kind of gets, if I can take a step back to, the mission of the ALCF. So we stand up these resources that are orders of magnitude larger than anywhere else that's available, to help enable that community, to help enable those in the community who need that scale of resources. And so this is not to say that high performance computing clusters at universities or companies are small. They're not. They in themselves are extremely powerful to support their users. But there are those in the community who just need more compute. They need more memory. They need more resources for the problems that they're trying to tackle. That they can't afford to take approximations, or that the data sets they're working with are just that large. Those are the researchers that we're trying to help enable, to help them continue pushing forward on the science. And so that's why we stand up these large machines, both us, the Argonne Leadership Computing Facility, and also our sister facility at Oak Ridge, who also has an exascale system.
So we have a few good questions that I think have come across. We've had a couple folks ask sort of what the power requirements are for our data center for Aurora, and sort of what it takes to run these kinds of machines at this scale.
So the older machines like Theta, what was that? That was, I think the peak was around 3 megawatts. And that was a 10 petaflop system. And so a 10 petaflop CPU system at, around 3 megawatts. It's not really a fair comparison with what I'm about to say. The Aurora, with a peak performance of more than 2 exaflops, 2,000 petaflops, so around 200 times more powerful. It has a peak power draw of around 60 megawatts. So it's big increases in power, big increases in performance. It's a little more complicated than that. And really the peak number is a number that very few, the machine does not usually run in that mode. Science applications don't stress every single component in the system as hard as that to drive up that peak usage. So want to be careful with those numbers, but these are big numbers.
One question was as far as units, is it megawatts per month, per day, per hour? Do you know?
No.
Mm-hmm. We have a capacity of 60 megawatts to run at, right?
Yeah.
Mm-hmm.
At any point in time, we were able to support that level.
Mm-hmm. Another question, Nicholas asked, what happens to decommissioned machines? Can we buy them?
Yeah, that's a really good question. The challenge is in part the packaging. That, if you can bear with me, that this is a lot of compute resources in a very dense packaging. And so this is not exactly a blade that I could take in and put underneath my desk. And so that's one of the challenges, is that you can't necessarily take an individual blade and work with it. You tend to need to take a big chunk of the machine, like a rack at a time. But it's also the rack is one thing, but then also there's the infrastructure, the electrical to power it, the water and the plumbing to cool it, service nodes to keep it operational. And so it's challenging to just say take a rack or two and move it off site. What tends to happen is other computing sites that have similar architecture and similar parts will take some of our racks as spare parts if they want to keep their machine up and running for longer. In a few cases, I know of some hardware going to, say, a university to help with teaching, but I think that was a rare example, again because of the packaging. And so sadly, a lot of it just gets recycled as much as possible.
So one other question, we've taught thinking about getting on these machines, sort of the allocation programs that we have. One question was at how long after an inquiry for a director's discretionary, for those who don't know what it is, it's our smallest allocation program. Should one wait before you actually get on to these machines, or sort of what's the cycle for that?
So the director's discretionary applications are processed on a weekly basis. And so within a week or so, you should hear back. And anecdotally, I can comment that as long as you are conveying in earnest an idea that you want to pursue on the machine, you're very likely to get the time and the access. And so then once the project is approved, it's the getting that user account access. And so that depends on individuals. It could be on the order of a week or more. I'm not really answering the question, but it is a short period, say, maybe within a month or so, that you'll get access and you'll be able to SSH into one of the machines here. And then really from there, you are free to do as you like, to explore the machine and then see if it's a good fit for the work that you're doing. And then the thing that I would encourage for anyone who does pursue that is that recall that there is a large number of folks in the building who are here to help to provide support for anything that you need. It's just like one of those nuggets of information I hope people take away from this.
Yeah, definitely. Okay, one other question that is, I think, always an interesting one and almost always asked is sort of the cost of building Aurora and maintaining these. So obviously we have the cost electrically we've sort of addressed, but I guess maybe my framing of the question is like, why do these machines exist at a national lab versus at a university, as far as that sort of thing, the cost piece?
Yeah. So, I mean, one reason for the national labs is to solve big problems. And then so we're able to solve problems that are difficult for, say, individual universities to solve. And so we have the infrastructure and the teams here that we can support installing, say, a 2 exaflop machine today. And so really, cost is hard. There's if you Google, your favorite web browser, you can search and find numbers like 500 million associated with the project. And so I think the only takeaway I would grab from that is that these projects are at the scale of hundreds of millions of dollars. And that's not only just for the technology and the development of the technology and actually having the hardware that you can touch, but there's also that people element and the software that has to get developed. And so Aurora is a 10+ year project from start to finish, give or take. And so, the people, time, and effort across multiple facilities, ALCF, HPE, Cray, Intel, in addition to a lot of the research community, where we're supporting some 50 science applications today with early access, in addition to a number of other teams. And so there's a large contingent of folks that are helping to make this possible. And I think all of that helps to make a dollar amount hard to nail down. But these are expensive machines. These are big machines. And these are tools that the national labs can help provide to help enable the community.
Okay, one last question, recognizing we're just over time. Leanne asked, it seems like there have been several new supercomputers at the national labs in the past couple of years, looking at Perlmutter, Aurora, Frontier. Will this continue?
Yes. I mean, we're already in the process of thinking what the next machine will be. We, ALCF, the Oak Ridge, who had the Frontier exascale system, they're already thinking about what the next machine will be. Perlmutter was mentioned, so NERSC, they're already in the process of figuring out what the next machine will be. And so just as we tried to finish the install of the latest and greatest machine, we're already trying to figure out where the community is going and what the community needs are to design the machine that for science problems that Aurora won't be able to tackle. And there are a good deal of problems that we're confident Aurora won't be able to tackle because we just need that much more compute power. These are fun problems to have.
Yeah. Okay, cool. Thank you so much, Chris, for showing us around both on video and also sort of showing Aurora as your backdrop.
Yeah. And so again, my first virtual tour, please give Paige and others feedback, what went well, what didn't go well, so we can try to improve this. I very much appreciate that.